Hello everyone, welcome to the lecture again. In the last few lectures, we integrate the Newton's law to find out the velocity and position of a particle as a function of time. Now, we are going to look an alternate procedure that is based on energy. Using this method, certain class of problems can be handled more easily and we do not need to integrate the differential equation. This is known as work energy method. Before we go deep into the work energy method, let us look at the conservation laws. So, let us first look at the conservation of linear momentum. So, we have the Newton equation of motion summation F equal to mx double dot or ma, and acceleration A can be written as dv by dt. Suppose m is constant, that is the mass is constant and does not vary with time. In that case, I can take m inside and I can write down d by dt mv, and we know that mv is the momentum. Therefore, we have summation F equal to dp by dt. Now, from this equation it is clear that if summation F equal to 0, then rate of change of momentum is 0, that means P is constant. So, what does this mean? This implies that if the resultant force acting on a particle is 0, then the linear momentum of the particle is constant or remains constant. Now, let us look at conservation of angular momentum. The angular momentum is defined as moment of momentum. So, angular momentum is the moment of momentum. So, when we take moment, we multiply by r and then momentum is mv. Let us denote it by L. Therefore, L is moment of momentum p. So, I can write down as L equal to r cross m times v, because p is mv. Now, let us look at dl by dt. So, dl by dt is d over dt r cross mv, and we know d by dt of a vector cross b vector is dA by dt cross b plus a cross dB by dt. Let us use this identity. So, we have dl by dt equal to dr by dt cross mv plus r cross m dv by dt. Okay. Now, dr by dt is the velocity, and v cross v will be 0. Therefore, we will have 0 plus r cross m dv by dt is nothing but the force. So, r cross f, and we know that r cross f is the moment or torque. Okay. So, we have dl by dt equal to r cross summation f, which is nothing but moment or torque. This implies that if the moment or torque is 0, then dl by dt will also be 0. Okay. Therefore, L becomes the constant of motion. So, let me write it down in the text. If the total torque acting on the particle is 0, then angular momentum is conserved. Okay. Now, let us look at the angular momentum in Cartesian coordinate. So, as we saw, the angular momentum L is the moment of momentum r cross p. Therefore, let us write down in the matrix form I j k, r is x, y and z, and momentum p is m times v and m is constant. So, let me write down m v x, m v y and m v z. Let us look at component by component. Therefore, L x is the coefficient of I. So, it becomes m is constant, y v z minus z v y, and L y becomes m z v x minus x v z, and L z becomes m x v y minus y v x. Now, let us look at the angular momentum in polar coordinates. So, again angular momentum L is moment of momentum and P is m times v. So, I can write down as m r cross v. Now, v in polar coordinate can be written as v r cap plus v theta cap, where v r is the coefficient or the component along the r cap direction and v theta is the component of the velocity along the theta cap direction. Now, the first term here is the cross product of vector r with r cap and they are in the same direction, therefore, it will be 0. So, this term will be 0, therefore, we have m r cross v theta cap. Now, we know the velocity in the theta cap direction is r theta dot theta cap. So, therefore, L becomes m r square theta dot and its direction will be in the theta cap direction. So, therefore, L is m r square theta dot. Now, let me show you that the angular momentum is conserved in the motion under central force. So, we are going to see that the angular momentum is conserved in motion under central force. So, the central force is defined by a force which is always directed along the r cap direction. So, the force F in the form of some function of F r and then its direction along the r cap is a central force. So, let me mention that the force direction is always towards or away from a fixed point. This is the definition of the central force. So, just now we proved that dl by dt is r cross F and F is the central force, therefore, it is going to act in the r cap direction and it will have this functional form. So, let me put F equal to F r cap. Now, vector r cross r cap, they are in the same direction and there is a cross product. So, therefore, it will be 0. So, F r into r vector cross r cap, which will give you 0. So, that means that dl by dt is 0, therefore, L is conserved or the angular momentum is conserved. Now, let us prove another identity and the statement is following: for the motion under central force, the rate at which the area is swept out by the radius vector is constant, or the aerial velocity dA by dt is constant. This is also known as Kepler's law. Now, let us prove this statement. So, just now we saw that under the central motion, the angular momentum remains conserved. So, conservation of angular momentum, that means that d by dt of L is equal to 0, and we also saw that in polar coordinate system L is mr square theta dot. So, I can write down this as d over dt of m r square theta dot equal to 0. Now, m is a constant, so therefore, d by dt of, and let me multiply by half, r square theta dot is equal to 0, but m cannot be 0, therefore, d by dt half r square theta dot is equal to 0. Okay. Now, let us see what is this quantity. So, let us say a particle is moving under the central force, and at some times its position vector is r, and after some times the position vector changes by d theta. Therefore, this distance will be r d theta, and therefore, the area under this triangle dA will be half r d theta, or dA equal to half r square d theta. Therefore, dA by dt will be half r square d theta by dt, or I can write down as dA by dt equal to half r square theta dot, and 1 by 2 r square theta dot, which is equal to dA by dt, I can put it over here. So, I have d over dt dA by dt equal to 0. This implies that dA by dt is a constant of motion, or dA by dt is equal to constant, and this was the statement that the aerial velocity is constant under central force motion. Now, let us revisit the concept of work. So, the work done by the force, let us say F, during the displacement dr is du equal to F dot dr, and if you want to find out total work u, then you have to integrate F dr. Let us look at it for the case of friction. So, suppose I have a block and I apply some force. Because of that, this block moves by a distance of, let us say, x. Okay. And because it is on a frictional surface, so therefore, the frictional force will act on it. Let us say the kinetic friction is mu k, therefore, the frictional force will develop in that direction and its value will be n times mu k. Okay. So, F will be n times mu k, where n is the normal force, which is decided by the weight of this block. So, you can see here that the block is moving in the plus x direction and the frictional forces are acting in minus x direction. Therefore, because of the frictional force, the work done will be the force which is minus mu k times n into the displacement. Let us look at the case of spring. Let us say I have a spring and a mass m is attached to it. Let us say this is the natural length of the spring. Okay. Now, you extend this spring by an amount x, then we know that the force F is equal to minus k times x. Therefore, u will be from 0 to x, because herein I fix my coordinate. So, let us say this is x equal to 0. So, 0 to x minus kx dx, and this will give you minus half kx square. Here the minus sign is because the displacement and the force, they are in opposite direction. Okay. So, this implies that the displacement and the force are in opposite direction. Now, let us look at the principle of work and energy. And let us start with the Newton's second law, which is F equal to ma equal to m dv by dt. To find out the principle of work and energy, we have to integrate this equation with respect to displacement. So, let us integrate with respect to displacement, that is dr. So, integral f dot dr equal to integral m dv by dt and dr. Now, dr by dt is nothing but velocity. So, we have 1 to 2 f dot dr equal to m is constant, integral v1 to v2, and dr by dt is v dv. So, we have f dot dr is the work from 1 to 2. So, let me denote it by u 1 2 equal to m. The integral of v is v square divided by 2. So, by 2, and let us put the limit. So, we have v2 square minus v1 square. Let us define the kinetic energy Ke. Let us denote it by T equal to half m v square, and this is the kinetic energy of the particle. So, we can write down u12 equal to T2 minus T1, or let me write down in the natural sequence. We have a particle which is moving with a kinetic energy T1, work 1 to 2 is done on it, then its kinetic energy becomes T2. Okay. Let us say there are elastic members which are included in the system. Okay. So, when the elastic members are included in the system, then the work energy equation can be written as T1 plus V1 plus U12 equal to T2 plus V2. Here V1 is the potential energy which include the gravitational potential energy plus elastic potential energy. So, gravitational plus elastic, and U12 is the work done by, let us say, all external forces other than the gravitational and elastic. This is the statement of principle of work and energy. It is based on the conservation of energy. It states that if T1 is the initial kinetic energy and work U12 is done on it, then the kinetic energy becomes T2 and the relation is T1 plus U12 equal to T2. Now, based on these concepts, let us look at the sum of the problems, and the first problem statement is following. A satellite is launched in a direction parallel to the surface of the earth with a velocity of 30,000 kilometer per hour from an altitude of 400 kilometer. Determine the velocity of the satellite as it reaches its maximum of 4,000 kilometer, and it is given that the earth radius is 6,370 kilometer. Now, in this question we have been asked to find out the velocity of the satellite. Note that the satellite is performing a central motion, therefore, the angular momentum will be conserved. So, let me state that the satellite is acted on by a central force, therefore, the angular momentum is conserved. Okay. So, angular momentum, as we have discussed, it is the moment of momentum. Let us apply that at point A and B to find out the velocity at B. So, we have L, which is moment of momentum mVA equal to RB cross mVB. Now, the mass does not changes, so therefore, that will get cancelled, and we have RA. So, RA you have to measure from the center of the earth. Okay. So, again the situation is following. You have the earth center here, this point is A and that point is B. So, this is your RA, this is your RB, and RA and RB are from the center. Therefore, RA is 6,370 plus 400 kilometer, and this is equal to 6770 kilometer, and RB will be 6,370 kilometer plus its maximum distance, which is 4,000 kilometer, and that comes out to be 10,370 kilometer. Now, let us put it above. So, we have RA into VA, VA is given, it is 30,000 kilometer per hour equal to RB is 10,370 into VB, and from here VB comes out to be 19,590 kilometer per hour. Now, let us look at another problem statement. An automobile of mass 1000 kg is driven down a 5-degree inclined at a speed of 72 kilometer per hour when the brakes are applied. Causing a constant total braking force of 5,000 Newton, and we have been asked to determine the distance travelled by the automobile as it comes to a stop. So, we have the following situation. We have inclination which is 5-degree and a car is moving on it. The weight of the car is going to act downwards. So, W is 1000 kg, which is 9810 Newton. So, we multiply it by the Z, and the braking force of 5000 Newton is applied. So, since the car is moving in that direction, therefore, the braking force will act in this direction and its value is 5000 Newton. Now, the normal force N will be perpendicular to the 5-degree inclination. So, this is the direction of N, and now we can use the work and energy. Let us say this car stops after travelling a distance d, and we have to find out what is this d. So, let us use the principle of work energy, which is T1 plus U12 equal to T2. Let me call this equation number 1. The T1, which is the initial kinetic energy, it is half m V1 square, which is half m is given, it is 1000, and V1 is also given, it is 72 kilometer per second. So, let us convert it into MKS unit. So, 72 into 1000 divided by 3600, this becomes meter per second, and of course, there is a whole square. So, this gives you 200,000 joule. Now, T2 is the final kinetic energy, and since the car comes into the rest, therefore, T2 will be 0. Let us look at U12. So, U12 is F dot D, and the braking force of 5000 is acting over a distance of D. So, therefore, D, and it will be minus because the force and the displacement, they are in opposite direction, plus we have the component of W along the inclination. So, it will be W sine 5 degree multiplied by the distance d. So, this comes out to be minus 5000 d plus W is 9810 sine 5 degree into d, and we know the value of sine 5 degree. We put it here, then you get minus 4145 d. Let us put everything in equation number 1. So, we have 200,000 plus U12 which is minus 4145 d is equal to T2 which is 0, and this gives you d equal to 48.3 meter. So, with this let me stop here. See you in the next class. Thank you.